Okay, so I'll keep this a short lecture. At least I'll try to. So we can end soon. The objective of this lecture actually is to introduce a very important formalism that we'll continue using for the rest of the course, which is the formalism of Feynman diagrams. Okay, so Feynman diagrams are just a convenient graphical mnemonic to capture whatever we did earlier using weak contractions. Okay. So let me just remind you of the results that we had, and then we'll look at how these Feynman diagrams work. Okay, so what did we derive last time? We derived several results. We derived we found that this was minus I g squared 1 by, make sure I have my signs right, k1 minus k3 squared minus n squared plus epsilon plus 1 by minus k4 squared. No plus epsilon not required because yeah. Okay, so this was in the case where we had psi going to psi, and there was an important factor up front which was 2 pi to the 4 delta 4 k2 minus k3 minus k4. Yeah. Okay, so this was the result we got in the psi dagger psi phi theory. Okay. There was a similar result we got in the case where in the phi 4 theory. Okay. And that looked much simpler. Okay, and then there was the result we got in the case of is a phi 4 theory. This is the case of psi dagger psi. Okay. In the second case, there's no ambiguity about what the different terms are because there's only one kind of particle. Okay. Okay. So these were the three results we derived in the previous class. Is this all okay? Yeah. Okay. And the way we derived them was we said we set up this problem in terms of this S matrix. We wrote this as time ordered product of e to the minus HIT. And then various interesting things happen. In fact, this one was pretty easy to derive. Okay. It's not good. Oh yeah, there's no K4 in that. Thank you. Yeah. There's no K4. Yeah. So this one was pretty easy to derive. There's no K4. Thank you. Yeah. There's no K4 in this setup at all. Because it just came directly from the weak contractions. But we already saw some interesting things happening in these cases, right? In this case, what was the interesting thing we saw happening? The interesting thing we saw happening was that the interaction actually had a lambda phi to the 4 by 4 factorial. Okay, and that 4 factorial all cancelled out, and we just got a minus I lambda. Okay, in this case, we actually had to work a little bit to derive this answer because first we found there was no first order term that contributed to it. So we had to go to second order. Then we had to use Wick's theorem. After we used Wick's theorem, we found there was only one term in Wick's theorem which contributed to this. But there were also some interesting combinatoric factors here. Okay, first there was, when we looked at Wick's theorem here, we found there were 4 possible contractions, 4 possible, terms you could get. There was one possible term in Wick's theorem, but after that, when you inserted that theorem, there were 4 possible ways you could contract the various fields with the external states. But that, kind of neatly combined to give you this kind of term, which basically involves some symmetry between K3 and K4. There was a factor of 2 that we got from the exponent, but that cancelled out. Okay. So what I want to emphasize here is that there are various combinatoric factors that simplified a lot when we did this analysis. So what we want to do now is find a different way of doing the analysis, which will use some graphical techniques, which basically has all of this inbuilt and in packaged. Okay. Okay. By the way, I don't know if is anybody on Zoom? Is a Zoom meeting on? Okay, fine. They can see this. I don't know. This board is kind of all white, but okay. If no one's saying anything, we will just proceed. It's pretty hot right now, but okay, good. So we now want a graphical mnemonic to understand this. Now I want to emphasize something. Okay, when Feynman diagrams were first developed, they were developed historically not in the way that we are learning them now. Okay, they were first developed as a way to genuinely understand quantum field theory, and when we draw the diagrams, we'll see the story that goes along with it. Okay, they were really developed as this is what's you have. So there were some stories that will go along with this. You had two fields, like with the third process we've written. Or maybe the top process we've written. You have two fields, they meet, they combine to give some virtual particle, or they exchange some virtual particle, and then that virtual particle splits up and so on. Okay, so there are various stories that went along with this, and people thought maybe this is the right way to write down these amplitudes, and then they checked it was consistent with unitarity and so on. The way we are doing it is quite different. Okay, the way we are doing it is, we are consistently doing some perturbation theory and then using Wick's theorem and getting it in a very systematic way. And then from here onwards, doing Feynman diagrams is just, basically just repackaging some of the combinatorics. So it's not very deep. This kind of formalism or this kind of perspective towards QFT was developed by Dyson after a lot of the results on QFT had already been obtained. So, a few years after that, in the late 1940s and 1950s, it was Dyson who really systematized a lot of this. And so what you now find in QFT textbooks really comes from there. Okay, not quite the early way in which QFT was developed, which was much more messy, but now it's now we have a much more systematic way of understanding this. Okay, so this is not quite how Feynman developed Feynman diagrams, the way we're understanding it, but this is how we understand it now. Okay. Okay, so they are just a graphical mnemonic from the way we're understanding them now. Mnemonic. Okay, and that they're just a graphical mnemonic to repackage Dyson series plus Wick's theorem. So that's all they're doing. So there's nothing very conceptually deep about what we are doing, but it's very useful. Okay, it's a useful calculational tool. But in principle, if you forgot how to draw Feynman diagrams, you could go back to doing Wick's theorem and just get all of those results just using Wick's theorem. Yeah? Okay, so what's the structure of Feynman diagrams? The structure of Feynman diagrams is that we have vertices joined by propagators. Okay. This is the uniform structure of all Feynman diagrams that we'll see. Okay, so these are mnemonics, and the mnemonics have basically they just have two ingredients. Okay, they have an ingredient of a vertex where things meet, and then that different vertices are joined together by propagators. That's it. Okay, there are only two basic ingredients, and then there are various rules you have to apply at the vertices. Sometimes, and then there are integrals you need to do. Sometimes, there are delta functions that leave you basically fix everything, so there's no integral you're left with. Sometimes there might be integrals you're left to do, but the basic structure is just this. Okay. Okay, is this clear? No questions? Okay, fine. Okay, good. So vertices are those that come from from a single insertion of hi. Okay, this is the general rule. Okay, so there could be many kinds of vertices, and you might have thought, given a theory, how do we know what the vertices are? The simple rule is that vertices are those where you look at one insertion of hi, and that gives you already the vertices. Okay, so in the phi to the 4 theory, what is hi? Hi is lambda phi to the 4 by 4 factorial. Okay, and what is the vertex? The vertex is just this. And you have to associate a value with this vertex, and the value in this case that you associate is minus I lambda. Not the minus I lambda by 4 factorial. Okay, you just associate the value minus I lambda. Okay, so the combinatrix you already take care of. How do you take care of it? Because from the kind of exercise that we did earlier that the 4 factorial is going to contract in different ways of contracting this thing with the external legs, and that will always happen because there is a symmetry of 4 factorial in these legs. Okay, therefore the value you associate with this vertex is just minus I lambda. Okay, is this clear? You're very quiet. I don't know what to make of this. Okay, fine. Okay, good. In addition, you're supposed to do something at the vertices, which is you're supposed to impose at every vertex energy momentum conservation. Okay, so we impose What does that mean? That means that you mark the momenta that come in here. A4, and you write down the factor that we have on top. Okay. Okay. Delta functions always come with a 2 pi to the 4. Every delta function comes with a 2 pi. Okay. And correspondingly, every integral comes with a 1 by 2 pi. Okay. So you shouldn't, there's no excuse for not getting the 2 pi's right. 1 over 2 pi always comes with an integral, and 2 pi always comes with the delta function. Yeah. Okay. Now, in fact, there's a way to do Feynman diagrams also in position space. Okay. But it's much easier to work in momentum space because it's much easier to impose, energy momentum conservation at every vertex. Okay. Okay. Good. Any questions about this? Okay, good. What about the phi dagger phi? Okay. Okay. So now you can guess that there are first of all 2 kinds of particles, right? Here there's only 1 kind of particle. Now in this case there are 2 kinds of particles. So we have to make up some notation. Now, what kind of notation can we make up? So one is, we have different kinds of particles just for. So you can guess that this is the phi particle. Okay. And then we have a psi and we have a psi dagger. Okay. So regardless of whether they are incoming or outgoing, we need some way of assigning, which one is a psi line and which one is a psi dagger line. Okay. So let's choose this. Let's choose the arrow so that this is the psi and this is the psi dagger. Okay. Okay, so this represents the psi line and this represents the psi dagger line. This is the convention. You could have chosen to draw the arrows the other way. Okay. And then we mark the momenta. This could be K1, K2, be K3. And we assign to this the value minus Ig times 2 pi to the 4. Which is the basic answer that we got there. Yeah. Okay. Notice, by the way, maybe I should say one more thing. There's also a factor of minus I that I'm including with all these vertices. And the factor of minus I comes from the fact that, you know, what appears in these insertions in Dyson series is e to the minus I hit. Okay? So that's where this minus I comes. Okay? The Hamiltonian interaction itself doesn't have minus I lambda, but you know, you always get a minus I because what you're expanding is time ordered product of e to the minus I hit. Okay. Okay, so that is the vertex in the phi dagger phi, psi dagger psi phi theory. Okay. What about propagators? Well, there are two kinds of propagators. One is the phi phi propagator. Do you remember where we saw the phi phi propagator here? We saw the phi phi propagator here because when we did the Wick contraction, we found two insertions, right? We found a psi dagger psi phi and a psi dagger psi phi, and then we contracted the two phi's together. Okay? So this propagator is just literally the contraction of the two phi's. It's just the value of the time ordered product of phi of x, phi of y. Okay? However, because we are working in momentum space, we only want its Fourier transform. And you remember what its Fourier transform is. There's something a little annoying here, which is when we are talking about the phi-4 theory, it's a little inconvenient to draw dashed lines, but let me do it for today. Okay. What's annoying is that we have a scalar particle. Here we have only a scalar particle, so it's convenient to draw solid lines. Here we're using the dashed line to represent the scalar particle. Okay, so I'll try and be consistent. If you're only talking about the phi-4 theory, we won't bother drawing dashed lines. Okay, we can just draw straight lines. Okay, this is what is the propagator here? Well, the propagator here is just, you know, plus I by k squared minus m squared plus I epsilon, where this is the momentum k. It doesn't matter if you draw the momentum the other way. It's still k squared minus m squared. And then there is this propagator. This is the time ordered product of psi of x it's just literally that guy, and it's the same, it just has a different mass. Okay, the I epsilon is important to write here. It won't be important in the first set of things we'll do, but later when we do loops and so on, the I epsilon will become quite important. Okay, so you should keep the I epsilon with the propagator in the Feynman rules. Okay, so there are these two kinds of propagators. And then what are the rules? Well, the rules are, you know, you just join these vertices together with propagators. You know, it's like one of those you know, plug and play things, right? So you just join these vertices together with different propagators till you get a diagram that represents the process that you want. Okay? And then you're done. You read off the value of the diagram just by assigning these different values to the vertices and to this, and then you're done. Okay. Okay, good. Is this clear? Let me see if there's something else I wanted to say. The arrows on the line. The arrows, you see, there are two kinds of particles, right? One is a psi and one is a psi dagger. So the arrows and the lines are, we are using that to differentiate which is a psi and which is a psi dagger. So we are saying that this, you know, is you can assign a psi particle here and a psi dagger particle here to this.
how to keep track of that? I mean, arrow towards the line, towards the vertex.
You have to make up your notation, but that's one way to keep track of it. Okay, good. Okay. The other thing is, the last rule is, integrate over all undetermined momenta. Or just or all undetermined momenta, fine. So you see, sometimes it will happen that these integrals become trivial, as we'll see in a minute. It will happen in a few lectures from now that these integrals will not be trivial. There will be some momenta which will not be fixed, and then there will really be integrals we'll need to do. For now, in today's lecture, all the integrals we'll see will just be trivial. Okay, good. Okay. So let's get our previous results, using this process. Okay. So for instance, well, the 5-4 result that we got, we had some results here, and so the three results we got recently, right? One was this 5-5 to 5-5, and that's just obviously you get this answer. One was psi dagger psi, there was a psi dagger going to this, okay, and that's just obvious. We get the right answer. Okay, good. So now let's see if we can get this nucleon plus nucleon going to nucleon plus nucleon. Okay. Okay. So what are the different kinds of diagrams we can draw? We have to attach those kinds of lines, right? So K1, K2, okay, K3, K4. Okay, this is one diagram that we can draw. Okay, so you have psi particle that comes in, psi particle that goes out, psi particle that comes in, and psi particle that goes out. Okay. Okay. What is the value of this diagram? The value of this diagram is, so we have minus Ig, okay, from here we get a 2 pi to the 4 delta 4, let's call this momentum P, okay, delta 4 into K1 plus K1 minus K3 minus P, okay, into I into P squared minus M squared plus I epsilon, okay, into minus I into G into delta 4, okay, of K2 plus P minus K4. Okay, and this P momentum for now is undetermined, so I'll integrate over it. Okay. Okay, is this clear? Yeah. Okay, but now notice we have two delta functions. Sorry, there should be a 2 pi to the 4. We have two delta functions, okay, and we have two delta functions, and there's one integral. This integral is setting P equal to K1 minus K3. This delta function is trying to set P equal to K4 minus K2, right? So the two delta functions together set K1 minus K3 equal to K4 minus K2, or K1 plus K2 is equal to K3 plus K4. Okay. So after you do the integral, this just becomes, there's a minus ig, a plus I, so you get a minus ig squared into 1 by K1 minus K3 squared minus, or not m squared, minus m squared, fine, minus m squared plus I epsilon 2 pi to the 4 K1 plus K2. Okay, so that's the answer. And we see we got the answer in a much more simple way than the answer that we had to do previously. Okay, okay, what other diagram can we draw? Right, so there's another diagram we can draw, which is where you mark this to be K4 or this to be K1. Okay, so you could draw this diagram. Okay, and you could mark this to be K3, K4, and this to be K3. Okay, okay. Now, okay, this diagram can also be drawn another way. You'll see it sometimes drawn the following way, okay, which is you decide how you want to set the ordering. Okay, so you decide you want K2, K1, K3 on top and K4 here. And then the way you do it is you join this to K3 and you join this to K4. Okay. So these two are the same thing. Okay. All I've done, the advantage of this, the slight advantage of this is that, you know, the momenta are marked in the same place. So if you're not looking very carefully, K3 is always on top, K4 is always below. Actually, if you're slightly better about this, you should mark the momenta in some anti-clockwise way. Okay, but that's yet another convention that I never follow, so we'll not follow it. Yeah. So you could have marked this as K1, K2, K3, K4, okay, rather than doing this. But that, okay, okay. So this diagram is the same as this diagram. Okay? They're just drawn differently. Do you see this? Yeah. Okay, good. And this is given by what? It's same kind of expression. Okay, but something is different. What's different is this momentum here is P, and this time it's delta 4 of K1 minus K4 minus P. Do you see why? Because this vertex has K1, K4 and P. And then we have K2 plus P minus K3. And as previously, you know, this is just interchanging K3 and K4, so it doesn't do anything to this overall delta function. But it does make this K1 minus K4 squared minus M squared. Okay. Okay. These are the same answers we got previously, but it's much more efficient to do it by drawing these diagrams, okay, than by trying to do, you know, this the Wick contractions. Okay. Now there's a story that goes along with these diagrams. Okay. These diagrams, you know, also suggest a story, but the story is really just a story. Okay. You should not take, you know, you shouldn't take, I think, the story very seriously. Okay. The story is as follows. Okay. Once upon a time, you know, there was this nucleon. Okay, there were two nucleons, and they were going on their way, and one of them emitted a virtual particle, a virtual meson, which was caught by the other one, and then they proceeded to go on their way. Okay. Usually, it's not said so poetically, but you just say, you know, there are these two particles, and they exchange a virtual particle in the middle, and they go on. So you, The once upon a time is embellishment you don't have to have, but you could use it. Okay. Same thing here. What is this? Here it is just that you have the out state, okay, and in the out state these are really Bose particles. Okay, so when they exchange the particle the meson with K1 throughout a particle which had K1 minus K4 instead of K1 minus K3, and therefore you ended up with this state. Okay? The fact that you have this diagram and this diagram, these diagrams always occur whenever the two particle states are identical, the two final states are identical, right? Because remember, after all, the particles are indistinguishable. So it doesn't make sense to say that this particle K1 is the one which went into K3 after exchange, because it could well have been the one that went into K4. There is no real distinction between this final state and this final state here. Okay? So these kinds of things always occur. And the story here is this is sometimes, this is called an exchange. So you exchange this particle in the middle. Okay? And that's how, there was an interaction. Okay? Now this is some way to think about it physically, but remember that precisely what's happening is that you have these contractions, and that's what you're looking at. Okay, so if you like to think about it physically, you can think about this in terms of an exchange, if you ever get confused with that, just go back and think about the fact that there are these contractions that you're doing, and that gives you these terms. Yeah. Okay, good. Are there any questions about that? Okay. So let me now, okay. So now that we have this formalism of looking at Feynman diagrams, we can do more processes, okay, which would have been pretty hard to do if we were just trying to, do weak contractions, okay. So the other kinds of processes that we can do are processes where you want to, oh, by the way, let's say I was doing n bar plus n bar going to n bar plus n bar. What would be the amplitude for that? Yeah, instead of n, if I had n bar. Huh? Right now it's all n, yeah, but let's say it was all n bar. Yes, okay, so does anything change in the answer or? No, nothing changes. It can't change, right? Because these two things are related by symmetry. So it certainly shouldn't be the case that the interaction between two n's is different than the interaction between two n bars. If that was the case, it would break the symmetry. Okay? So by symmetry that the fact that you have two n's, you change everything to n bar must be the, so the amplitudes must be the same because there's an unbroken symmetry in the theory. Okay? And the diagrams that you'll get will just be the ones which you get by reversing all the arrows. Okay? So if you reverse all the arrows, you'll get n going to n bar. Okay? So if you just reverse the arrows here, you'll get a set of diagrams which will instead be the diagrams that will represent n bar plus n bar going to n bar plus n bar. Okay? Okay, good. So now let's look at a different set of diagrams. Okay, which look like n plus n bar is this process allowed or not allowed? It is allowed, right? Because the final states, initial states have the same charge. Okay, so you tell me what diagrams I should draw. Okay, so how should I draw it? Maybe I'll draw this vertex here. Should draw this vertex. Okay, and let's call this K1 and let's call this K2 n. Okay, and what's the diagram? I connect this. Okay. Okay, and then this looks like this is the outgoing K3 and this is K4. Sorry. Okay, so this is the incoming psi, this is the outgoing psi, this is the incoming psi bar, this is the outgoing psi bar. Okay. Can you think of any other diagram? Why don't you guys think of a diagram and try and draw it if you can find any other diagram? Okay, what's the value of this? First, let's get the value of this. What's the value of this thing? So I won't write all the p's. Okay, we know there's going to be a minus ig squared. Okay, that's going to come because it's the same factors. Okay, minus ig gives you a minus sign, and a plus I from the propagator gives you a minus ig squared. And what should I write here? K1 minus K2. Sorry, you're right. I should have drawn it this way because I had, but thank you. I should have drawn this one this way. Sorry. Yeah. This is, sorry. It was K1. Sorry, I got confused. I should differentiate between the arrows of the particles and the arrows of the moment. K1 and K2 are the ones which are ingoing. Yeah. So this is K1. Sorry, I apologize for that. K1 plus K2 squared minus m squared. Okay, and then there's the usual energy momentum conserving delta function. Okay, can you guys think for a minute to see if there's any other diagram that you can think of, or if this is the only diagram? This is an exercise. Just think for a few minutes and see if you can do it. Did you get it? Or is it the only diagram, or there's one more diagram? Okay. Did everyone get it, or? You see, what do you want, right? What you want is that there should be, you just want these external things to be this way, right? That's what's telling you the external particles. So you don't care what's happening inside. So there's another diagram, and the other diagram is this, which is you draw this and you draw this one going out. So this is K1, this is K3. Okay. And then you have K2, and you have here K4. So notice, by the way, here what you call K3 and what you call K4 is fixed. Okay. In what we did previously, in the diagram that we had previously, the two final states were identical. Here the two final states are not identical. Okay. K3 is the momentum of the outgoing nucleon, and K4 is the momentum of the outgoing antinucleon. Okay. There's no choice about that. However, Here what can happen is that you can have this nucleon and it can emit some exchange which is absorbed by this antinucleon. Okay. So this is a different diagram which gives you minus Ig squared into 1 by K1 minus K3 squared minus n squared. But it also has the same energy momentum conserving delta function. Okay. Okay. Now the story that goes along with this diagram and this diagram is slightly different. Okay. The story that goes along with this diagram is you have a nucleon and an antinucleon. They come in, they annihilate to produce a virtual meson of momentum p. Okay, so they both cease to exist for some time. After some time, that virtual meson decays back into a nucleon and an antinucleon. Okay. That is the story that goes along with this. So the story is two particles meet and annihilate to create a virtual meson which decays back into two particles. Why is this a virtual meson? Why is it not a real meson? It's not a real meson because this particle in the middle with momentum p doesn't actually have p squared equal to m squared. Okay? It just has p being whatever the sum of these two momenta are. That's why it's a virtual particle, not actually satisfying, not actually sitting on mass shell. Okay? But if you want to think about this process, you can think of this as this process where you have this particle which is kind of off shell for some time, and then it decays into doing something else. If you don't like these stories, you don't have to think about them. Okay, this is just a term in the Wick contraction. Okay. What about the story that goes along with this? The story that goes along with this is different from the story that goes along with this. In that case, the story that went along with both diagrams were the same. In this case, the story that goes along with this is two particles exchange a meson and continue their way. Okay, so you have two particles which come in, they exchange a meson and they continue their way. So you have a nucleon and antinucleon, they never actually meet and annihilate, they just exchange a meson and they keep going on. Okay, so you see there are two kinds of physical things that can happen. The nucleon and antinucleon can meet, produce something which has zero charge, which can then decay back, or the nucleon and the antinucleon can just exchange something and keep going. Okay, but the final answer is the sum of these two. Okay, the final answer is there's a common factor. Okay, into okay, and that's it. That's the final answer. The final answer is you sum all of these processes. Okay, and this is what quantum mechanics tells you to do. You have to sum over all possible intermediate processes that can happen. Okay, so you sum over this and you sum over this. They look like they're different, okay, but you have to sum over them. Okay. Okay, is this also clear to everyone? Okay, very good. So then let's study a third case, which is okay, since you're all familiar with this, and since I don't have so much more I want to say, let's do this as an exercise, okay? Okay. So I'm going to get someone to do this on the board. Let's see who volunteers. Okay, let's do 5 plus n goes to 5 plus n. Okay, there are two diagrams for this process as well. Will someone come and draw one diagram? Someone want to volunteer? Okay, who will volunteer to draw one diagram? Anyone? Because all of you are looking down in your notebook suddenly. I want to volunteer to come here and draw the diagram. Okay, first you can try and do it and then you can come and draw it. You want to try? Okay. You want to try? Okay, come and draw one. Write its value also. Okay, very good. And can you write its value and also tell what the story is? Okay, very good. And what's the story that goes along with this?
The phi part, it's the meson, right? So the meson and nucleon exchange and anti-nucleon, and then they.
Oh, good. Yeah, that's right. That's right. So you have a meson, and you have some nucleon, and the nucleon, okay, it emits a virtual nucleon. It has to emit a virtual nucleon. It can't emit anything else. It can't emit an anti-nucleon. It emits a virtual nucleon, and this virtual nucleon is absorbed by the meson, which turns into a real nucleon. Okay, and after emitting this virtual nucleon, this thing turns into a real meson. Okay, sit. Good. Yeah, so is this clear what's happening? It's kind of confusing, but this is what this diagram is telling us. You have a meson, you have a nucleon. Okay, the nucleon emits a virtual nucleon. Okay. By emitting a virtual nucleon, it turns into a real meson. Okay. And this thing, this virtual nucleon is absorbed by this meson, and the meson by absorbing a virtual nucleon turns into a real meson. Okay. So the identity is not fixed. The fact that you have these interactions tells you one kind of particle can change into another kind of particle. Okay. So, and that's what's happening even upstairs. You can have two things which annihilate. You can have mesons and anti-mesons which annihilate and lead to become nucleons and anti-nucleons which annihilate and become a meson. Okay. So this is important, and in fact this is one of the reasons, if you remember, why we started studying quantum field theory. You can have processes of this kind where kinds of particles that started and begin are not quite the same. Okay, good. This is one diagram. Can anyone draw the other diagram? It's pretty simple actually. It's related to this one. You want to try? Maybe do it in the right hand side, so you'll have more space. Okay, but the arrows have to have a continuous direction.
But the chart should be.
Yeah, good. Yeah, good. Mm-hmm. No, it's okay. K1 and this was marked as K2. Yeah, it's fine. Okay, good. It should be squared, K1 plus K2 squared, and it should be minus mu squared because the particle that's propagating in the middle is this. Yeah? Okay, good. Excellent. So this is the other diagram. Okay. And here the story that goes along with this is that you have a meson, okay, and you have a nucleon. The meson and the nucleon, they meet and they both turn into a nucleon, a fat nucleon, which is carrying an additional meson. After some time, this meson, this nucleon which is carrying it, can't carry it, so it gulps out the meson again. The meson gets released, and you come back to a real nucleon. Okay. So this is the story that's happening here. Okay. It's a different story, and of course the answer finally is the sum of these two. Yeah. Okay. So it's pretty simple to draw these diagrams. You can draw, you can consider other processes if you like here, and you can draw these diagrams. In some cases, you might get, um, uh, you can get different kinds of diagrams. The only thing to remember, I guess, is when you draw these diagrams, and if you have a case where the final states are the same, you have to remember about the symmetry. Yeah. Okay, so that's good. That's basically what I wanted to do today, which is introduce you to this technique of diagrams and explain these Feynman rules. And we've already in today's lecture managed to compute some simple examples of various processes associated with these simple theories. Yeah. So if you look at other kinds of theories, you can easily write down the vertices that you have, and put those vertices together. It's very simple, as you can see, and generate all kinds of interesting processes. Okay, we'll see that we'll have to correct this thing as we go forward, but this formalism that we've not yet understood various subtleties in this formalism, and there'll be subtleties that will appear. Mostly the subtleties that will appear will be in the case when some of the momenta are undetermined. Okay, at this point there was not really any integral to do. We were marking this as p, but this was kind of fixed to be k1. Here to be k1 minus k3, there to be k1 plus k2. There was not really any option about it. But in some cases it will happen that the momenta that you have will not be fixed, and there'll be loops, and then we'll need to worry about how to enhance this formalism. Yeah. Okay, so that's what we wanted to discuss today. In fact, I'm glad we finished a little early. Are there any questions about this? Is there any other process I wanted to discuss? Not really. Okay, so that's all I wanted to do today. We can stop here since this is an extra class anyway. We don't have to go on for the full time. You have a question? Yeah. Huh.
Is it physically same to interchange the K3 line with the K4 line?
The K3 line.
The dotted line in the above and the
solid line below. Wait. No. Oh, sorry. Thank you. The diagrams are marked differently. No. So you should have written this as K3 and K4. That's some convention thing. So this was K4. Sorry, guys. The two of you marked the arrows differently. Okay, so there was the outgoing meson had momentum K4. I didn't notice it. I should have noticed it. And the outgoing nucleon had momentum K3. Okay? And you're not allowed to interchange them. Okay? The K3 is the momentum of the outgoing nucleon, which was fixed in this diagram, and K4 is the momentum of the outgoing meson, and it's not the same to interchange them. Okay? So these two diagrams are not labeled consistently. This should have been K4, this should have been K3. It doesn't change this value because this is going to be K2 plus K1 anyway. Yeah, which is the same as K3 plus K4. Yeah.
And could have I drawn the dotted line above and the solid line below? Leftmost dot.
Yeah, but it's the same. What is it? I mean, you mean this way? Like rotate this by? Yeah, sure. But that doesn't. I mean, what's important is not what you draw below and above. What's important is what momenta you assign to them. If you draw it this way, like that, that's just obviously some matter of convention, right? I mean, a matter of whether you like the arrows to be below or not. But what's important is that you mark this as K2, this is K1, this is whatever P, and what should I mark here? Should I mark K4 below or K3 below? No, I have to mark K3 below for it to be the same. Okay. If I mark, you see the K3 is defined to be the momentum of the outgoing nucleon. I can't mark it to be K4. If I mark it to be K4, that will be a different process where the outgoing nucleon has momentum K4. Okay, so I have to mark this to be K3, and I have to mark this to be K4. Now, in this case, it might look as the same because the vertex has no dependence on the momentum. It would be completely wrong to mark this as K4 and mark this as K3. I mean, completely wrong in that you choose a convention, you stick with it. Okay? So the convention that you chose, in fact, here was that K3 was the momentum of the nucleon and K4 was the momentum of the meson. Okay? In fact, that's the convention you chose. And then you have to stick with that convention. Okay? So you could, whether you draw it below or above doesn't have any meaning, but what momentum you mark with it does have a meaning. Okay. Are there any other questions? No question? Yeah. What is the maximum? What is the maximum number of processes? You just have to see how many diagrams you can draw. So in this case, you know, I mean, how do you know if there's one diagram or two diagrams or three diagrams? You don't know ahead of time. You have to draw the diagrams and see what there are. For instance, let's consider a slightly different theory. Okay, let's consider a theory which is a, sorry, since you asked, okay. Let's consider slightly different theory. So it's not, there's no rule that says you have to have three diagrams or two diagrams, okay? You could, I can't believe this. So this one, do not disturb. So you see, let's say I consider what's called the phi cube theory. Okay? The phi cube theory we're not studying really, but it's something which has three scalars interacting this way. And I try to study the same process that we had earlier. K1, K2 goes to K1, K2. Then you could draw this diagram. K3, K4. Okay. Or you could draw this diagram. Oh man, I can't believe this. I thought it's on do not disturb. I know I'm getting so many calls. This is directed TIFR or something. Okay, let me try and ignore it. If they try again, I have an override in my do not disturb if people try to call me repeatedly. Okay. Okay. Or you could also draw a third diagram, which is this one. So you could draw this to be K3 and this to be K4. So in this case, you know, for this 2 to 2 scattering, there'll be three diagrams that you'll get. Okay. How to know is there's no a priori way. You just have to do it. So we've also considered a case in the phi-4 theory for the same process that is only one diagram. Okay. So there's one diagram, three diagrams, and two diagrams. Okay. So there could be, there's no rule that tells you how many diagrams you have. Yeah? Okay, are there any other questions?